Thank you, Andres. Thank you all for coming. So yes, I'm going to tell you what is this about, and everything that I'm going to say is joint work with Spencer Bachman from Vermont. And so the first, um, the first is like this here. The main problem, and it's so important that I just want to put it here, is very basic, and this is like a very general question, and this is the sort of thing that I will be interested. Just given P, I want to write it as a Minkowski sum of two polytopes or more. This is a very general question. I would like to do this in general. I would like to somehow factor the polytope, if you want. And this is a general question. Can you do this for a flow polytope, for an Alkov polytope, for a generalized permutoid, a matroid polytope? Pick your favorite polytope and try to make it simpler somehow. Okay? Okay, so this is what we would like to do at the end of everything. Like how to do this problem, and we will see that this innocent question will take us down a deep rabbit hole, and we will end up talking about other things, but keep in mind that this is the motivating question, so I leave it there in the board. Okay, so the Minkowski sum in general is easy to define. You can define the sum of any two sets. Particularly if you have two polytopes, you simply add them point-wise, all the pairs of points. And some people do this in the sense that I can take like one polytope, have the other one, and kind of like slide it through all of the points in the original polytope. That's one way of thinking about it, but the point is that if I add these two things, I add all possible pairs of points, and I take, the result is another polytope. It's not hard to see that if you add two polytopes, you get another polytope. Okay? So this is what I want. It's sort of easy to go forward, to multiply, to add Q plus R, but it will be harder to, given P, decompose it, or maybe decide that it's not possible. So some basic things, I'm saying that I want to decompose P using two other polytopes, Q and R. So some basic observations here are, if I take any polytope, let's say Q, and I add a point, so a point is a valid polytope, so zero dimensional, that thing will be the translation of Q by something. So some people will say that we do everything modding out by translations. We don't do that here, but basically, if I can translate back and forth, and those are kind of like in the background. Also, there is always some trivial things that you can do. Like P is equal to 1/2 of P plus 1/2 of P. This is because of convexity, P is closed under taking all the midpoints. So yes, that equality is true. And that means that you can always do that. If I just say decompose it, then sure, you can do it. You can say that P is equal to 1/2 of P plus 1/2 of P. So this is something that we don't want. So we are going to say that the composition is non-trivial if at least one of the factors is not an homotety of the original. Okay, so if the factors are really different, this will be, if you want to draw a parallel similar to like prime numbers, I want each of them to be different, not just multiplying by a unit, for example. And the last observation that is very key is that if I have a decomposition like this, P, Q plus R, then in every phase direction, I should also get a decomposition. And this helped me to study if this is possible or impossible. So what is this notation? So this is by this I mean the phase in direction C. What is a phase in direction C? So let's say that I have a polytope P, and I have a vector C that you can think of as a direction. So let's say that I'm just simply pointing, and I put my finger in that direction, and I say, what are the farthest points in P along this direction? So who has the largest dot product with C? So in this case, this is chosen in a way that maybe this whole segment is maximized, is the farthest, the set of the points that are the farthest along the C direction, and that gives you an edge of the polygon, and in general, that's the definition of a phase of a polytope in general. You just choose any direction, you point, and you pick the points in the polytope that are the farthest in that direction. So in general, if you have a decomposition, then if you restrict to any direction, you will get that the composition of the face in that direction is equal to this face plus this face. Okay, so you can always decompose. So I want to describe what is like a prime polytope in this case. So we are going to call it indecomposable if it has no non-trivial decomposition. By that I mean that if every time that I write P as Q plus R, then both of them are, or at least one of them, which implies both of them are an homotopy of P. Okay? It's not clear that you can always do that. So it's not clear when you are indecomposable or not. The first very simple example is a triangle. Okay? There is no way to write a triangle as a sum of two polygons. You can convince yourself of that quickly. So a triangle, the only possible summands, we are going to call them summands. The only possible summands are homotheties of the triangle. Okay? In general, because of the property that I said that you can restrict to faces, if a polytope has all the two-dimensional faces triangular, then it is indecomposable. That's weaker than being simplicial. So for simplicial polytopes, there is not, you cannot do it. So this question, I mean, a lot of polytopes are, famous polytopes are simplicial, and for a simplicial polytopes, there is nothing to do. It's indecomposable. You cannot break it in a non-trivial way. Okay, so triangles are indecomposable. Simplicial polytopes are indecomposable because somehow they are covered by triangles. But we can relax that property a little bit. Pyramids are always indecomposable. So for example, the Egyptian pyramid has 3 triangles and a square. But you can sit down in this example and realize that, well, there are 4 triangles. The face below is a square, not a triangle. But because the triangles can only be an homotopy in a summand, then it has to be that this guy is also like a square. So in this case, there are a lot of triangles, not all of them, but a lot of triangles covering the 2 skeleton, so it becomes indecomposable. To jump to some interesting examples, you can maybe recognize this as an example of a matroid polytope. And indeed, if you take a connected matroid and you take the matroid polytope, that thing is indecomposable. That was proven by Guggen in the 70s. And the reason has something to do with triangles. When you think about matroid polytopes, the 2 faces are either triangles or squares, and that plays a role in the proof. And there are a lot of triangles, so if you have a lot of triangles and some more arguments, you are indecomposable. Okay, so let me give you one result that we have. So this is, I am very interested in this. Like, what other examples of indecomposable polytopes are there? It's hard to prove that something is indecomposable. So every time that we get some example, I'm excited about that. And so that's the most basic question. So try to decompose it or show me that you cannot do it. Okay, so for the last slide, we have one example of something that is indecomposable that we proved with Spencer. So it's a very general thing. I have any polytope, and I have the vertices of the polytope. Now I put them 1 dimension up. So I put every vertex, comma 1 dimension up, and I take the sonotope of adding all of those, the segment from the origin to each of the vertices, but raised by 1. Okay, that thing will be a sonotope that looks like this thing, the Gherkin building, and so that, by the way, the sonotope is super decomposable because by definition, I'm saying let's add segments. Of course, I can Minkowski decompose it. But we say now take this thing and let's take the last coordinate. This is Python notation for -1, the largest coordinate, at least 1. So basically, take a machete, split it here in the floor, and take everything up, like the building. So in the building, you can see that you all have these sonotopes, you all have these parallelograms, but here you did like some cut and you got some triangles, okay? And one of our results that we need for later and for other reasons, we realized, well, this thing is indecomposable. And actually, yeah, let me leave it like that. So this thing is always indecomposable. So one example of this, that maybe I wish I had a better picture, but I can take a square, but the square that is like very symmetric with respect to the origin. So 1, 1, and all of the other 3 vertices. and I can put it in dimension 1 more in dimension 3, take the sonotope. That sonotope is a famous polytope, the rhombic dodecahedron. That guy is decomposable, but what we are saying is if the gherkin is cut one of the, take everything that is a level like more than 1. So basically in this case we are removing one vertex, and that thing ends up being indecomposable, which is interesting because if you look at the faces, there are triangles, there are 4 triangles, but most of them are parallelograms, and parallelograms are super decomposable. So this is an example in which there are triangles, but not enough triangles, and this thing becomes indecomposable. Okay, so this is one example, and you can do it for any polytope. Yes?
Sorry, can you explain again how you're just removing a vertex?
In this case, yes, because this thing, everything goes from 0 up, and I'm saying take everything at the level 1 and up. So in practice, it's removing a vertex. But I write it like this, like, okay, take the intersection with the hyperplane of 1 and up. In practice, I remove a vertex.
Okay, so in this picture, you're just going to pick any vertex to remove. And then in this picture, that is decomposable, right?
That is indecomposable. That's what I'm saying, that these guys are always indecomposable. Which is kind of like, that's like the magic. The sonotope is obviously decomposable, but once I truncate it, it's not. It becomes prime.
Right, wait, is this one truncated or not? I think that's...
It is truncated already. This is the gherkin, because there was a vertex here, and I truncated. I maybe should have prepared a better picture, but these 4 triangles were meeting here in a vertex, and I cut that vertex. Okay, so usually it is hard to prove that something is indecomposable. Okay, so what are the tools to study these problems? So I didn't even tell you how we prove that, but then the techniques and what I want to show you today is, okay, what is the theory behind all of this? And mainly talking about the problem translating it to a different language using supporting functions. So what is the support function of a polytope, or any convex set in general? If we have a polytope in some real vector space, then we can have a function that goes from the vector space to the real numbers, and that function is related to the faces. I choose a direction, again I point, and I look not at the point that reaches the maximum, but at the maximum point. So what is the maximum dot product between C and points in the polytope? This is a number, so I'm just, the question is how far can I go in that direction and still get something in the polytope, okay? So this is a support function. This is a function that any vector, it gives me something. Some boundary cases will be, what if C is 0? So if C is 0, I'm getting the maximum of 0, which is the whole polytope. This is related to the fact that the whole polytope is a face. Well, this is the function that depends on P, but P also depends on the function. You can define that P is equal to all x's in the vector space, such that when I point in that direction, this is at most that function. So this is almost like a tautology, but it is an important one because that means that if I have P, I have the support function. But if you give me the support function, I can define P. So they are both completely determined by each other. Okay? That's good. So maybe instead of looking at polytopes, I can look at these support functions. And people in convex geometry do this all the time. So there are theorems classifying the support functions of convex sets. This statement is for polytopes in particular. So here I have this function that I created depending on the polytope. I need to define it. Obviously, I need to know P. But in general, I can give you any function from V to R and try to detect, is this coming from is this a polytope function or not? And there are classical conditions. You need to be, first of all, piecewise linear. I'm going to say more about that in a second. But this is related to the fact that it's a polytope. If it wasn't a polytope, there is no piecewise linearity. And I need this property for every x and y, which is called subadditive. In general, I need that the function is convex, and the definition of convex is different. I'm using, there are some, this is really important that I'm talking about a polytope here, okay? And this is one of the reasons why people say, okay, now I can simply talk about functions, not about polytopes. And the idea will be, because also there are these properties that are key to us and are not very hard to prove, which is that the sum, if I have this function and this function, the point was sum of this function, the support of Q and the support of R is the support of Q plus R. and the support of dilating P is simply lambda times P. This is not hard. This is saying that the maximum over a sum of two polytopes is the sum of the maximums. And this is like very easy once you go back to the definition. And because of this, we can say, well, okay, maybe there is a different question, which is, instead of decomposing this, give me HP as a sum of two functions that at least, well, that there are polytopes, of course, but let's take it weaker. Let's forget about subadditive, and let's say at least give me HP, the function, as the sum of two functions that are piecewise linear. Okay, this is a relaxation because being piecewise linear is not enough. We need piecewise linear and these two in order for it to come from a polytope, but let's focus on piecewise linear for 1 second. Okay, now piecewise linear how? And we will see an example soon, but piecewise linear means that the function has some regions where it is equal to a linear function, but in different regions it can have a different linear functions and it will glue on the boundary. So it's a continuous piecewise linear function. Okay, there is a criterion proven by Shepard. There is a criterion for this. So basically, this is in Grunbaum's book, chapter 15, the first part of chapter 15. He says, this is a very natural question, and there is an answer, theoretical answer to this. Q is a summand of P if and only if something. Now, we want to relax this thing a little bit and say that talking about something being a weak summand, because I want the set of summands to be a cone. So I want that if I have two summands, I add it and I get a summand. And I want that if I have one summand, I can dilate it by 10 or 100 and it's still a summand. But then, of course, if P is very small, that will not be true. So we define a weak summand if Q is a weak summand of P if not Q plus R is equal to P, but maybe a dilation of P. Okay, this gives me more flexibility. I don't fix P, I fix P, but I give some room for dilation by a positive real scalar. And the theorem, which doesn't say this, but is equivalent to this, is saying that this characterizes Q is a weak Minkowski summand, with weak, of P if and only if I look at the normal fans of P and Q, and the normal fan of P is finer than the normal fan of Q, or people say the normal fan of Q is a coarsening of the normal fan of P. This really needs weak, because the normal fan doesn't know anything about the size of the polytope. So there is an answer to this. By the way, because of what I said before, you can also think of it this way. I have HP, I have HQ, and I want to define somehow who is R. R should be like the difference. So P minus Q, if I say P minus Q, in this talk, I really mean HP minus HQ. And this is a polytope. I will say that this ends up in an R so that P is equal to Q plus R, if and only if this function is like the support function of a convex polytope. Now this thing is both of them are piecewise linear, that's fine, but then the key will be that Q is a summand if and only if this thing is subadditive. So that will be something something to prove, and this is related to this criterion. So this is the tool that we have to check whether something is a summand of P. And this has something to do with normal fans, and I don't want to, so I'm not going to define normal fan, but maybe we will see in one example what is a fan. But in using normal fans, we can translate most of these questions, and we really care at the end about the fan. So I told you that this was the main question, but in theory, it's easier to, first of all, look at P up to scalars, and also up to normal equivalence. So I really care about the normal fan of P. If I have the normal fan of Q and R, I simply get so how is the normal fan of a sum? Is the refinement, the intersection of all possible cones. So if P is indecomposable, we are saying that this is impossible to do unless one of these guys is a homotopy of P, which means that they will have the same normal fan. And what we are saying then is that P is indecomposable if and only if its fan is, there is no word for this, so let's create a word, uncoarsenable. I cannot coarsen it with the normal fan of another polytope. Okay, this point of view makes the link between these are polyhedral subdivisions. So a fan, you can think of a fan as I have the whole space, and I'm going to subdivide it in cones. A general polyhedral subdivision of a polytope, let's say, we have a polytope and we subdivide it in other polytopes. There is like a poset by containment, by refinement and coarsening, and the finest subdivisions will be triangulations. At the level of fans, the finest subdivisions of the whole space will be a simplicial fan, where every cone is already simplicial. But on the opposite end of the spectrum, if I have, for example, the cube, and I'm looking at subdivisions of the cube, I can look at triangulations, and there are a lot of open questions about triangulations of a cube. This is the opposite. This is not triangulation. This is the largest subdivision that you can have, a subdivision that is uncoarsenable, that the only way to coarsen it is with the whole polytope. At the level of normal, with normal fans, we are saying something like that. Give me a fan such that there is no way to make it coarser. And of course, this is a very hard problem, either in this flavor or in the flavor of polyhedral subdivisions. Okay, but this means that if P, so this means that because of this equation, or because this theorem, I know that if Q is, if I'm looking for a Minkowski summand of P, then this fan is a coarsening of this one. Means that the cones are unions of cones of P, and that means in practice that when this thing about being piecewise linear, I was omitting that, is piecewise linear on a fan. But because of that theorem, if Q is to be a weak Minkowski summand of P, then the support function is piecewise linear on the same fan. So it's no longer, so here I'm saying piecewise linear somewhere. There are some pieces where the function is linear, but now, because of this theorem, I can say, well, there are some pieces where the support function of P is linear, and I can think of the support function of Q being piecewise linear on the same, being linear on the same pieces. It's part of the same fan. Okay, that's good. That's good. That means that we're looking at piecewise linear functions on the fan that is the normal fan of P. If P is simple, or equivalently, the normal fan is simplicial, then a piecewise linear function is just a bunch of values, so it becomes a vector, a finite vector. What do I mean by this? So this is the example. I need a piecewise linear function in R2. Okay, so this is, I have R2, the whole plane, and I need a function that takes any point and spits a point, spits a real number. Okay, and I want it to be piecewise linear. Okay, piecewise linear, this will be an example of piecewise linear. Maybe it's this formula for the xy here, or this formula for the xy here, and I have to make, to be careful that they agree on this line, and there is a different linear function here, and these two agree on this line, and these two agree on this line. So a piecewise linear functional has like a lot of information. I will need to give you one linear function per cone. But the key insight, the very, very key insight to make this computational, to implement it in Sage, is that this function is completely determined by three values. Let's say that my fan is this thing. So I split the whole R2 in three cones, but I also have the cones that are the intersections. So I have three two-dimensional cones, three one-dimensional cones, and one zero-dimensional cone in the origin. And the rays, the one-dimensional cones, these rays, we are always, let's say here we are dealing with a rational polyhedra. So there is a canonical generator, like the first lattice point that you hit. So we have, in the ray, we have a canonical generator, a minimal generator, which will be 1, 1 for this, 0, minus 1, minus 1, 0. And once I decide which value I want my function to be in these 3 points, then I can uniquely extend my function to be piecewise linear. This is very key, so let me just spend time here. So now my function, instead of being a whole function, I'm reducing it to a vector that has 3 entries in order. So it's 2, minus 5, and 4. But if I need a function here, a linear function, and I know the value on this guy and this guy, and they form a basis, that's why we are assuming that this guy is simplicial, because they form a basis, there is a unique function that is 2 in 1, 1, and 4 in 0, minus 1. That unique function is 6x minus 4y. And we do that for every cone. Okay? very key, that is determined by finitely many values. And the consequence of this is that the space of all piecewise linear function becomes finite dimensional. Okay, because basically in this case it's just 3-dimensional, it's just 3 numbers that I can add and multiply by a scalar. Okay, so we are talking about piecewise linear functions. If I fix the fan and I say all of the linear functions, all of the piecewise linear functions, these form a finite dimensional vector space. What is the dimension? Well, if it's simplicial, I can really do whatever I want. There is no, in this example, I can put any numbers, 2, 4, minus 5, they could be anything, and I extend it uniquely. So there is one decision for each ray. Good. If it's not simplicial, then it's still finite dimensional because you have to choose one value for each ray, but now you are not free. They have to satisfy something in order for a linear function to exist. So it will still be finite dimensional, but what is the dimension? This is very unknown. So this will be, so this is not known. What is the dimension of this? There is no really a good formula. There is there is not much to say. If it's simplicial, then it's the number of rays. If the fan is simplicial, then it's the number of rays. Else, we don't know. And again, another problem, just give me a polytope, compute that dimension. I think that's an interesting problem. Being indecomposable is equivalent to this thing having dimension 1. So, for example, so I'm talking about the fan being simplicial. So if I'm doing this for a simple polytope, I know that there will be a lot of dimension. If I'm doing this for a simplicial polytope, so the fan will be, well, the dual of a simplicial, that dimension is going to be 1. But in general, I was telling you that it's hard to detect when a polytope is indecomposable. At the level of fans, it's hard to know when this dimension is 1. That's just, there are very few theorems about that. Yes?
So it looks like in the previous slide that it was 3-dimensional.
3.
It was 3.
3, I have 3 decisions to make.
Right. But doesn't this correspond to a triangle?
Good point. I was trying to sweep that under the rug and I got caught. Yes, this is false. This is false because
is it like non-trivial one?
There is a linearity space. So
yeah.
Okay. Yes. So
okay,
sorry. This is
you're modding out by the linear ones.
Yes, I didn't want to do that, but the thing is that here there are 2 directions in which you can. So this is a triangle, and for the triangle you can either dilate it, one option, or translate it. And I kind of don't care about translation. So yeah, but good point. Good catch. Yeah. So ignore this. Because I didn't want to, I don't want to, I really want piecewise linear functions. Some people will say modulo the linear functions, which will be the equivalent to translations. I don't want to do that. So I have the space of piecewise linear function, which is a vector space, finite dimensional. I can compute it in Sage. Now, all the time I'm talking just about PL. Now I have to go back to the world of polytopes, and I need not only a piecewise linear function, but it has to be subadditive. So this is a subset. That subset ends up being a polyhedral cone, okay? It's not clear, maybe it's clear that it's a cone, or it's clear that it's something polyhedral because, oops. The conditions on being subadditive, they look like inequalities, but the way I wrote them, it looked like infinitely many inequalities, but you can prove that this thing is polyhedral, is a polyhedral cone. This follows from the work of many people, but let's say Macmillan's in the 70s. Now, this polyhedral cone, you can compute it in Sage. This is coming soon. This is in development, hopefully this year, because there are a lot of, so people have looked at this. There are a lot of criteria about how to compute these cones, what are the inequalities of these cones, and it all is very concrete, and we can compute everything and put it in Sage, hopefully this year. Not making any promises though. But again, computing this cone is also very interesting. It's a variation of the original question. Knowing the precise cone is also kind of hard. In few examples, this cone is nice. For example, in the case of the permutohedron, we will see that later, that polyhedral cone is the cone of submodular functions, which is like a very well-studied cone in optimization. In general, this thing is hard to compute. We can do it in Sage, but it's hard to theoretically say something about it.
Is
it closed?
Yes, because so the boundary consists of things that, let's do one example. For example, this guy, the square, what will be a summand of this? I need everyone that has, let's say, the same normal fund. If it's the same normal fund, then it can be any rectangle. So the same normal fund is the interior. The boundary is when it's not the same normal fund, but maybe it collapses to this or this. So when we say weak Minkowski summand, yes, we are taking it. We are taking the boundary. But the problem is that this cone has linearity space, because for any piecewise linear function, I can add a linear function and it will still be piecewise linear and additive and all of that. In the world of polytopes, this means if I have a summand, I can translate it by the dimension of the ambient space and it will still work. So there is some linearity space. So talking about rays is tricky. You have to say like quotient out the linearity space or something, or invoke the canonical decomposition in linearity plus cone plus polytope or something like that. This is a bit of a problem, but let's not worry too much about that. But yes, there are some translations there that make this thing non-pointed. But if we mode out by translations, it becomes pointed. Okay, so after everything, so we're halfway. Okay, so I wanted to do this, but then I started talking about support functions, and I want to decompose the HP, the function, as a sum of two other functions. And okay, how can we do that? So I have P my polytope, sigma the fund, and really what I want is, and not just doing it 2 times, I would like this decomposition to be full of indecomposable polytopes. It's like if I'm having a number like 20 is equal to 5 times 10, but I want that 10 I can keep decomposing. So ideally, I want to take P and not just the sum of 2, but maybe the sum of several polytopes, and hopefully indecomposable, because otherwise I can keep decomposing. Okay? Now, algebraically, what do I want? I have the piecewise linear functions of sigma, which is a vector space, and I want a basis of that. Abstract functions, I'm only requiring them to be piecewise linear, but in order for this to have something to do with polytopes, I want that my bases are support functions of summands of P. So I want a basis, but the functions have to come from polytopes. Hopefully, my basis is full of indecomposable polytopes. This is something that we cannot do in general. We can only do in 2 special cases, but that will be the dream. Like, I give you any polytope that is normally equivalent to P, that has certain normal fund this, and I want to write it down as in a unique way as a sum of certain polytopes, like the building blocks for this. I don't care. There is another variation of this, and this is why it's cool to use the support functions. I don't care if I get negative signs. What I'm saying is I find a basis, so let's say that when I have a basis, there is a unique way to write HP as a sum of, let's say, these 3 functions. If they are a basis, then there is a unique combination, and that combination may be negative. So 3 minus 4, 1. That could happen. And that is not bad news, because this can always be translated into, I put all the positive in one part and all the negative, I pass it to the other side. And this will happen as functions, even only if this happens as polytopes. So the fact that we get negative combinations is part of the algebra trick here. I don't particularly care. So if I want to, maybe P is Q plus R minus something else, and that means that I am adding something to P. I add to P in order to get a sum of the other ones. So the negative ones, I don't care. This is what we gain from using algebra, that we are allowed to go negative if it's necessary. Okay, this is what we would like. Now, can we do it? In general, no. The hardest thing is being indecomposable. Being indecomposable is a complicated property, but the dream scenario, Minkowski dream space, let's call it, is this, the famous case of generalized permutohedron. Okay, so what is this thing? So P is the permutohedron, the normal fan is called the braid fan. Okay, so now you look at all polytopes that have the braid fan as the normal fan, so that gives you some piecewise linear functions, and we can have a basis consisting of polytopes. This basis is famous, let's call it the Postnikov basis, and in this case, it's very concrete, and this is what we would like to generalize, but we cannot, but this is what we want to generalize. The basis in this case are simplices, but instead of, so we have the convex hull of some subset of the dimension. So basically, these guys are the faces of the standard simplex. I take all of these faces, so this makes sense whenever I have any subset that is non-empty. Empty, by the way, empty doesn't really make sense here as a summand. When I look at the normal fan of empty, that doesn't make sense. So empty is not allowed here, and I have to take all possible subsets that are non-empty, and I get a total of 2n minus 1. Now, then you look at what is the dimension of this thing? This thing is simple, this fan is simplicial, so I want the number of rays. The number of rays is known to be 2 to the n minus 2. So there is a mismatch. This is another detail that I'm putting under the rug, and is that, yes, it should be 2 to the n minus 2, but I was being imprecise. The thing is that this thing has a linearity space too. There is an equality that this thing satisfies, so there is one more parameter, there is one more degree of freedom in that space. So it's not minus 2, it's plus 1. So it's actually the number of rays plus the dimension of the linearity space. So in this case, these two things match. And not just that, these guys are indecomposable trivially because they are simplices, okay? And there is a theorem, and this is the theorem that we would like to generalize. People write this generalized permutation in this way, what they call a Z polytope, and this is basically the support function. It's saying like, write it with inequalities at most blah and one equality. And there is a theorem that takes you from the support function to the sign decomposition as here. This is the dream scenario. You give me a polytope given by inequalities, you give me the support function, and there is a theorem to reveal how to write it as these building blocks. And this going from C to Y is inverting a matrix. In this case, it's a Mobius inversion. It's very clean. This is like the best case. Okay? We would like to have something like this, a basis of indecomposable polytopes, and that we can like invert the certain matrix to be able to explicitly, from the support function, write it in terms of that basis, which means that any polytope can be written as a sign decomposition of the elements of the basis. So that's what we call a Minkowski basis, and this is the best scenario. Now, we cannot do this in general. This is very hard. It's every step here, everything that works perfectly well here is it goes away if I move something a little bit. So, okay, so I cannot do this in general for any fan, but I want to generalize this example. So I want to take what is true in this example and try to expand. So one thing that is true is that this fan is actually the barycentric subdivision of the normal fan of the standard simplex. So this thing appears as the barycentric subdivision of something. Okay, what is barycentric subdivision? So there are like two dual things. So I'm talking either about fans or about polytopes. If I have a polytope and I have a vertex, I can truncate that vertex. What do I mean is that I take a certain direction that is given by the sum of the two normals, and I can push a wall. I can push an epsilon inside the polytope. That will be the truncation at distance epsilon. One of the reasons why we don't like to use polytopes but fans is that if you work with this version, you really need to be careful about who is epsilon. Epsilon has to be small enough. And if you have several epsilons flying around, a big mess. But here, the normal fan, the dual operation is I have a cone, and in that cone, I perform something called a stellar subdivision, which means I have two rays that create a cone, and I add all of the rays in the cone. In this case, I add these two rays and I get this, and I split my two-dimensional cone into two. That will be a stellar subdivision. You can do this in any dimension. And this will be also central stellar, because you can do this with any vector, but in order for everything to make sense, it's better to be easier, it's better to just take the sum. Okay? And this is related to the fact that this direction, I take it as the sum of these two directions and I push. So I can either truncate a face or do a stellar subdivision. And the thing is that this braid fan, you can obtain it by taking the standard simplex and start truncating all of the faces, or its normal fan and start doing a stellar subdivision in all of the faces. This is a whole other topic that I cannot say too much right now, but you have to subdivide in the barycentric subdivision of a fan, you have to subdivide all of the cones. So you do them one by one, and you go down in dimension. So first you do a stellar subdivision in all the full dimensional ones. In the resulting one, you do a stellar subdivision on the codimension 1 cones that were in the original fan, and so on. Then codimension 2, codimension 3, and so on. You end up with a fan that is called the barycentric subdivision. At the level of polytopes, is better. I like it for the pictures, except for the fact that I have to be careful for the epsilons. But here in the picture, I can say, well, let's truncate all faces, all of them. So I have vertices, edges, and 2 faces. But now I have to do it going up in dimension, because these two things are dual. So what can I say? For example, I can truncate this vertex, and I get something like this. And then after doing this, I can truncate this, this, and this. So I can like shave off them, I can chisel them, and I get some corners that look like this. And I have to do that in all of the other vertices. Okay?
You do all vertices first and then all edges. You do all vertices first and then all edges?
Yes. So here I only did like a corner. You have to do all vertices, then you do all edges, all of the original edges, and then all of the faces. The 2 faces, you can truncate them. It doesn't change too much. You just push it a little bit. This is similar. So in algebra, they call it the blow up of a certain subvariety. And if you blow up something of codimension 1, you don't do anything by the universal property. But that's at the level of fans. If the polytope does change, if you push with the wall a little bit. Okay, so let me change the goal and say, I cannot do it in general, but at least if I want to generalize the case of generalized permutohedron, I start with a polytope S, let's call it the seed polytope, has a fan, and then I do the super iterated truncation, so all vertices, all edges, blah, blah, blah. Dually, I take the barycentric subdivision of sigma, and I want a Minkowski basis for that gamma. Okay, now the number of rays of a barycentric subdivision is known that is, you get 1 ray for each face of the original polytope, or 1 ray for each cone of the fan. Okay, so at least on the numerology, I can say, okay, my bases need to have 1 element for each face of the original polytope, or 1 element for each cone of the original fan. And this makes some sense. So the first theorem is, okay, take S and subtract the truncation along epsilon for every face. Do that for all faces. This is a basis. When I say this minus this, I really mean the difference in the support functions. This is not what I want. This is not exactly what I want. This is just a linear basis for the set of piecewise linear functions. Okay? We have the right number, but we have to prove that they are linearly independent. That's not that hard, but that takes some work. That is some intense linear algebra. By the way, okay, let's see maybe one example. No. Well, this is not very important, just for the experts. There is something called the nested complexes by Fechner and Kozlov. This is related to the wonderful compactifications of hyperplanar arrangement that Galen was talking this morning. And there is something where people don't blow all of the faces, or they don't truncate all of the faces, or they don't divide all of the cones. They just take some of them, but that some of them has to be, let's say we're talking about cones. Don't subdivide all of them, subdivide a subset, but that subset has to be closed under taking joints. And people study that. That's something called the nested complex of that. And one thing that we can prove is that if you do that, if you don't do all of the barycentric subdivision, but a subset, well-behaved subset, then it is the same as taking the refinement of individual stellar subdivisions at the level of fans. At the level of polytope, this means something like, if I do a partial truncation, and this is related to nestohedra in the case of generalized permutohedra, then I am adding single truncations of, this is more or less it. This theorem is implicit in the work of Fechner and Kozlov, and also Mantovani, Padrol, and Pilot. This condition, maybe I want to say something quickly, in order for us to learn something about how the truncation works. In the case of the cube, what I was saying is this is a corner of the cube, and I first truncate the vertex, and then I can truncate the neighbors. Okay? This is the right way of doing this. Now, I can have this guy. What happens if I want to truncate this edge? I can do it, but it will look something like this. And now I want to truncate the other edge. But now it really, like the point is that when I do this truncation, this kind of messes up in the neighborhood of this one. So these two they share this vertex that was not truncated, so then it kind of depends. Then you will get something, I don't know, a strange picture, maybe hard to draw, but the order will matter. So doing first this and then this will be different from the other order. So I don't want to truncate an edge and another edge unless I already truncated the intersection. That's at the level of faces. At the level of cones, I don't want to subdivide two cones unless the common containment I already subdivided. Okay, but this is not too important. But okay, this is important. This is why we like the single truncations. There is another problem, and is that these truncations are almost by definition never indecomposable. So, for example, if I start with the permutohedron here, the hexagon, so the seed polytope, this is the iterated truncation of that triangle. What am I saying? I'm saying that the basis somehow is let's do truncations on all faces. One vertex, another vertex, another vertex, and the truncations along the three sides, we push them a little bit. This pushing is taking care of the translations, for example, because if I start subtracting the pushings, I'm getting like an epsilon translation in three directions, and that takes care of the up to translation statement. So this is what we are doing. But the dream case was not that. Was all of the faces of that thing. So the three segments, the three vertices, and the original one. Okay, so we look at this and we say, what can we do? We need to fix this. It cannot be just the truncation, but the idea is that the truncation is too naive. Maybe we have to push further, because if instead of doing that, I push further, I do a strong truncation, then I get something like this. Maybe if I keep pushing until I cannot push anymore, I get this. If I push in this direction, I get this. And for the facets, now it makes sense. If I push the facet all the way here, I get a vertex, and a vertex. So it seems like this truncation that I say, okay, move it a little bit with an epsilon, don't use epsilon. Now we define a strong truncation. I'm going to truncate a face. The truncation will be something like this. I push gently a little bit, very little, so that I modify the normal fan a little bit. But the definition of the strong truncation, you can see, is a little annoying, the largest epsilon such that blah. But here in the pictures, I'm just saying, start pushing that facet in the same direction until you hit another vertex. If you hit another vertex, stop. You cannot pass a vertex, that will change the normal fan. So push until you cannot push further, and then in that case, you get that strong truncation. Okay. By the way, going back to question of Bennett related, when the polytope is smooth and primitive, so smooth was defined by Lewis, and primitive means that you are smooth, but also all of the edges have the same length. So all of them 1 or 2 or 3. Then this strong truncation is like removing the face. So when we did this strong truncation, it turns out that I touch all of the neighbors at the same time. So it's like I took away that edge from the convex hull and I take convex hull of the rest. And that always happens if you are smooth and primitive, which makes some arguments easier. And who is smooth and primitive, you may ask? Well, the standard simplex, we will see the product of standard simplices, the permutohedron is also smooth and primitive, and nestohedra are smooth and primitive. So it's crazy, but not that crazy. Okay, if we apply this method, if we apply these strong truncations to the standard simplex, then we get the Minkowski dream space. Okay, so now with doing strong truncations, we recover this. We recover this picture, at least until here. So we can recover these bases, and there was a bit of a confusion on how to generalize this, people thought like, oh, these are faces of the seed, faces of the standard simplex. It's true, but that's not the way to generalize it. We think they are strong truncations of the faces of the standard simplex. So if we do all the strong truncations, we get the dream basis. So that's good. So we are, at least in that case, we can prove it again. And in general, we have two results. One is product of simplices. We do it for arbitrary product of simplices. The bookkeeping is complicated, and there are a lot of corner cases depending on the dimension of each simplex. But let's put two simplices. If I have two simplices as the seed, so I take the barycentric subdivision of a product of simplices, then we have a Minkowski basis. We take the original guy, so this cross 0, 0 cross this, and we add all the strong truncations from all faces. I'm lying a little bit. This is almost true. For example, if I do it in the case of type B generalized permutohedron, that will be take the product, it's a cube. I have a cube and I do the barycentric subdivision of its normal fan. In the cube, I'm multiplying segments. A product of simplices, yes, product of segments, that's a cube. So in a cube, I'm saying like, okay, the idea is take the 3 lines of the cube, I didn't put it, the 3 lines of the cube and also add all strong truncations. This is one strong truncation of one vertex. This guy is indecomposable. Not too hard to prove, but it also requires some tools that I have not talked about here. So if you take any cube and you remove one vertex, the resulting polytope is indecomposable. It's kind of surprising. But when I remove an edge, I don't get indecomposable. This is not true, but I can make it into an indecomposable. I know how to decompose it. This is not what I want, but this is trivially a triangle cross a segment. So it's not a strong truncations, a modulo, a split that we can do canonically somehow. So, okay, to emphasize, we have a Minkowski basis when you have the product of simplices and you take the iterated truncation of that, or the barycentric subdivision of product of normal fans of the standard simplex. So, in particular, in type B generalized permutohedron, that means I start with the cube, I do the iterated truncation, and that normal fan that I get is the type B braid fan. And all of these methods that we've said create a new basis of indecomposables. Now, this was already done, and this is so we were late into the party. Jose Bastidas in 2021 has a basis. The basis takes more or less like faces of the cross polytope and do something else. And Eur, Fink, Larson, Spink, they also have a different basis, also with simplices, so it's of course indecomposable. And they really use this to generalize some of these algebraic geometric results for the type B case. We have a different basis, especially because our basis is not full of simplices, it has something else. And we believe, I mean, I care about these things intrinsically, I think they are nice. Now, if you're asking me for an application, they already did the applications. I think the support functions of these guys are better behaved, but I don't know. We could reprove what they did. This doesn't make a lot of sense. It's important for them to study the mixed volumes of the stuff that they have. So a natural question in the algebraic geometry sense is, what are the mixed volumes of the polytopes of this basis? Which is still an interesting question. And the other case that we can do is, now I take the barycentric braid. What do I mean? Now I take as a seed the permutohedron. So I start with the braid fan, and now I take the barycentric subdivision. Because this guy is the barycentric subdivision of something, this is a double barycentric subdivision, and in that case, we can do it. So we take a Minkowski basis, which is the original basis, the Postnikov basis, and we add, now we cannot, the strong truncations, they are very decomposable, so we have to tweak a lot of the stuff, and it's a longer story that I don't have time, but this is where, to complete this basis, we are doing some Gherkin. So we take some sonotopes, and these sonotopes, they come from root or edge polytopes, and we like truncate one vertex, and we do all of this together in the composable basis here. And this is with an eye of trying to okay, now we have this basis, but we would like to decompose certain known polytopes. So in this case, there is something called the permutoassociahedron, so we would like to sit down and write it as a sum of these guys. That is possible, we just need to figure out the coefficients. There is also more generally some polytope by Guy called there is some permutonestohedra, and all of these polytopes that are created like that, they can be written as a sine sum of these bases. So that will be like something interesting to do. And that's it. Thank you for your